One of the most important ideas in probability and statistics is the concept of a distribution. We will understand what a distribution is by picking up one of the most famous distributions called a Gaussian distribution and understanding it. Right? So you might have come across a shape like this, which looks like a bell-shaped curve. This is one of the most recognizable shapes in probability and statistics. And by the way, we just saw such a shape when we were looking at so if this is my petal length, the probability density function of my petal length of Setosa, versicolor, and virginica flowers actually look like the bell-shaped curves that are very representative of a Gaussian distribution. Right? So this is a very popular distribution that's used extensively in statistics, and we'll learn everything about it one by one. Right? So before we go and understand it, the bell-shaped curve that you saw is nothing but the probability density function of a Gaussian distribution, of a Gaussian distributed random variable. So let's assume x is a continuous random variable. Let's assume x is a continuous random variable, and if x has a PDF, right, a probability density function that looks like your bell-shaped curve, then we say x has a distribution which is a Gaussian distribution. I'll also introduce you some notation on how to represent what a distribution of how to represent the distribution of a random variable in a while. But before we go into it, you might ask, okay, why should I learn about this distribution? Because a lot of things in nature actually follow Gaussian distribution. Not everything, but certainly some very important things. So for example, heights of people, similarly weights of people, tend to follow a Gaussian distribution. Similarly, we just saw your petal length and sepal lengths, which are actually measurements of sepals and petals of real flowers. They all seem to look like bell curves. We'll see whether they're actually Gaussian distributed or not little later in this chapter. But for now, they all look like your bell-shaped curves, right? So Gaussian distribution occurs a lot in nature, especially in natural phenomenon like heights and weights. It is also connected to a very important idea in statistics called central limit theorem that we will learn a little later. But just take my word for it right now that it's extremely widely found distribution in nature, right? Having said that, you might ask, okay, why are we learning about these distributions? Why do I learn about these distributions? Why do I learn about these distributions? We will see why we're learning about distributions after we learn some properties of distribution and how it is useful. But in short, I could say that distributions are very simple models of natural behavior. Very simple models. For example, if you tell me that your petal lengths of Setosa flowers follow Gaussian distribution, let's assume we know that your petal lengths follow a Gaussian distribution. I can tell you a bunch of properties about your petal lengths without even having measured any of your petal lengths. So it's a very simple model to summarize all the information about a random variable or a physical measurement like a length or a height or a weight, right? So by the way, all of your petal lengths can be thought of, petal length, sepal length, everything can be thought of as a continuous random variable, right? And whatever values that you get are basically sampling from the distribution, right? Anyway, if some of the terms are alien to you, I promise you'll surely understand it. But before we go into it, let's understand Gaussian distribution a little more. I promise you by the end of this subtopic, you'll understand everything about distributions. But please bear with me. There are a lot of interconnected areas that we need to cover one by one slowly. Only at the end of it, we'll get the whole picture, right? So now I'm on a page of Wikipedia corresponding to something called a normal distribution. Gaussian distribution is also called as normal distribution. We'll see what is a standard normal distribution in a while. So this plot, if x is a random variable, if x is a continuous random variable, then this is your probability density function, right? So your probability density function of your Gaussian random variables look like your small hills or your bells, right? So if you look at it, on the top right here, you have a very nice legend, which shows you two values, mu and sigma square, right? So here mu is nothing but, so let's take the blue curve here, right? For a Gaussian random variable, Mu is nothing but the average value or the mean value. We learned about concepts called mean and variance, right? Mu is nothing but your mean, and sigma square is nothing but your variance. So if x has a Gaussian distribution, or if x behaves like a Gaussian distributed random variable, and if the mean of x, if a mean of x is 0, right, and if its variance is 0.2, then its PDF will look like this. Will look exactly like this, like your dark blue line here, like this dark blue line here. Now, what you could say is, what are these? Which basically means there's a very interesting thing, which is if you tell me your mean and your variance, your sigma square is nothing but variance. If you tell me that your random variable x follows Gaussian distribution, and if you give me its mean and variance, nothing else, you just give me these two values, I can tell you what its PDF is. Right? So these two values are called the parameters of the distribution. So your mean and variance are called your parameters of the distribution. So for example, you could say that, okay, I have my random variable petal length. So let's go and look at this data for a second. So imagine if somebody tells me that the setosa's petal length have a mean of 1.5. Suppose if somebody tells me that setosa's petal length follows Gaussian distribution. Let somebody. I'm not saying it is actually it actually follows Gaussian distribution. And if somebody tells me that the mean of these values is 1.5, and the variance seems to be small here, right? Let's assume the variance is I don't know. I think we computed it earlier. I'll just pick a value here. Let's assume the variance is 0.25. Right? Let again. This is all let. The moment you tell me that mu is 1.5 and sigma square is 0.25, I can quickly draw the distribution without having even seen one value of petal lengths of setosa. So if you just give me these two values, I know what the PDF looks like. As soon as I know what PDF looks like, I can compute my CDF, right? So all the information that is there in 50 observations can be summarized very succinctly by just using these two values, given the fact that, see, by the way, if I don't know that your random variable x or your petal length is Gaussian distributed, if I don't know its Gaussian distribution, these two values are not useful. So the first thing that I need to know is that my petal length is Gaussian distributed. If this is true, then all I need to know to plot its PDF is just the mu and the variance. Right? Now let's see how the shape of a Gaussian distribution changes as mu and sigma change. Right? So by the way, for your both red, so if you look at these three plots here, your blue, red, and yellowish plot here, all of them have a mean of 0. Right? All of them have a mean of 0. And as variance increases, so the variance of your blue plot is 0.2, the variance of your red one is 1, your variance of your yellow line is 5. So we do know that variance is a measure of spread. Right? Variance is a measure of spread. It's also called a scale in probability and statistics. Okay? So if my variance is small, then my probability density function, my PDF, is going to be peaked and thin like this. As my variance increases, my probability density function is going to get fatter and fatter and shorter, right? So at the same time, so that's what happens if your variance changes. What about your mu? If your mu changes, so for this green line here, your mu is at -2, right? So the peak of your hill in your probability distribution, probability density function of a Gaussian distribution, is often at mu. It's exactly at mu actually. So mu is the most often found value, because what is the height of in a PDF, the height represents how often we find these points, right? What is the probability of finding a value around -2? So in a Gaussian distribution function, the peak of your hill for your PDF is at mu. Right? So if somebody plots a PDF like this, and if I know that it's Gaussian random variable, that it's a Gaussian distribution, if somebody says this is 2, and if somebody says, then immediately I know, since this is the maximal value, Immediately I know that my mu is equals to 2, right? So let me introduce you some simple notation. Since we know that the parameters of a Gaussian distribution, are simply mu and sigma square, which is nothing but variance. Which means if you just give me my mean and variance, I can tell you everything about the probability density function of a Gaussian of distributed random variable. So it's often written like this. I'll just introduce you to some notation. Let's assume x is a random variable. I say that x follows a Gaussian distribution or a normal distribution with mean mu and variance sigma square. So how to read it? It is x, this is nothing but x follows, your n represents your normal or Gaussian distribution, right? And what are the parameters of my distribution? Mu here is my mean and sigma square here is my variance. So if somebody says x is normally distributed with a mean of 0 and a variance of 2, right? As soon as I see this, I can plot the probability density function of x with mean at 0, and we'll see how variance plays in this, right? Your variance probably will be here, and this will be -2 here, this will be -4, this will be +4, and so on and so forth. Okay, we'll see how to get this shape, right? So is the bell shape more understandable today? The peak of the bell shape is always at mu, and your variance, suppose if I have two random variables, let's just again take a quick example here. Let's assume I have a random variable x with a mean of 0 and a variance of 2. Let's assume I have another random variable y, again with a mean at 0 but a variance of 4. Then I know that my x is like this. If my x is like this, then my y would be fatter and shorter, right? Because y has a higher variance than your x, right? Variance basically talks about spread. So this spread is much more than the spread of your random variable x. So having understood this, let's go into some more mathematical details of a Gaussian distribution. All this is fun. We have seen the graphical part of it. We've understood the bell-shaped curve. But let's go into slight details of math. So if I know that x is normally distributed with a mu and sigma square, let's assume x is a random variable. It could be your petal length, sepal length, your height of students, or weights of students. If x is normally distributed with a mean of mu and a variance of sigma square, then I can quickly say that probability of x equal to some value x, small x. Remember, this is a random variable. This is a value. So let's assume if x is heights of students, then this could be probability that height of a student is equal to 160 centimeters. This is an actual value. That's why I wrote it in small x, right? You can write it as an expression like this. Probability of a random variable x being equal to a value x, small x. The small x could be 160 centimeters or something like this. This is a random variable capital X, right? So this is often in short written as probability of x equals to, this is a notation that we saw earlier, right? At the start of this chapter. It's a very simple notation to follow. So this is nothing but 1 by root 2 pi sigma exp minus x minus mu square by 2 sigma square, right? So of course this looks very, very daunting on the surface, but I promise you I'll simplify this for you. I'll give you the intuition, and I'll break this up and explain it piece by piece. Trust me, I will do that. I promise you that. Having promised you that, let's go and understand what is exp here. First, let's go and understand. Exp is nothing but e power. So exp of x is nothing but e power x. It is the exponent. It's the exponential function where e is the base of natural logarithm, right? So because it's harder to write this whole expression in the superscript, we just typically write it this way, right? But exp of x is nothing but e power x. You must have encountered this in your high school when you're learning logarithms, right? Now, having said that, to understand this function, let's simplify it. Let us assume that mu equals to 0 and sigma equals to 1, or sigma square equals to 1, which means sigma equals to 1, right? Let's assume this for a second. let's just assume this. So as to simplify and understand this math, then your probability of finding a random variable x equals to x. See, whenever I don't write it, all I mean is capital random variable x equals to x is 1 by root 2 pi. My sigma is 1 here, right? Exp of my 2, it's basically half here, right? Because sigma square is 1 and x mu is 0, half of x square, right? This is much more easy to digest, okay? So let me break this up again. So we assume that mu equals to 0 and sigma square equals to 1, and I'll explain you the details of, I'll explain you what this shape looks like, okay? So just bear with me. So what do we have here? We have probability of x equals to 1 by root 2 pi exp of minus half x square. So what does this mean? So if this was equal to y, right? And if you're trying to plot this function, let's try to plot this function, right? So this you can think of this as a constant, right? This is basically a constant, right? This is basically a constant, right? Because it's 1 by root 2 pi, so you can ignore that. This is also a constant. Sorry, you shouldn't keep the half is also a constant, right? So this is also a constant. So if you have to simplify this further, this looks like y equals to exp of minus x square. If see what I've done here is, first I've written this very crazy looking formula. I've simplified it by making my mu 0 and sigma square equals to 1, and I'm further simplifying it by removing the constants. What is the shape of this? If I have to plot this shape, right? Because by just removing constants, the form of the equation still doesn't change. When you plot this function, what you get is your bell-shaped curve. Now let me explain you what it is, right? Your mu, of course, is 0, right? And what it says is, so this is your x, right? So your mu equals to 0, right? So this is your random variable x. Let's assume this is y, which is nothing but probability of x, right? So your y is nothing but p of x, right? Now what it's saying here is this: as x increases, this is extremely important. As x increases, so let's assume my x is 0. At that point, I have a very high value here, right? If my x equals to 0, what happens to y? If my x equals to 0, it's e power 0. So y is going to be e power of 0 with these constants put in. So if I put in the constants here, what do I get? 1 by root 2 pi exp of 0. Exp of 0 is 1, right? So the maximum value here in this case, with the mu equals to 0 and variance equals to, and let's assume my sigma square equals to 1, then my maximum value here is going to be 1 by root 2 pi, right? Because it's a constant that I'm using. But just let's drop the constants to get understand the shape better. So what it's saying here is, so what is this? As x, so what happens as x increases? Let's understand what happens to y. As x increases, which means as you're moving on this axis, your y is going to reduce, right? Because this function, right? If you go and if we just look through this function here carefully, right? As x increases, what happens? As x increases, right? Your minus x square is going to reduce because it's negative, right? Your x square, this is what it is. Your minus x square is going to reduce. As minus x square reduces, exponent of minus x square is also going to reduce, right? So the first thing is, as x increases, right? As x moves goes away from 0, that's what I meant. As x goes in this direction, your y is going to reduce, as you see in this plot. First observation. Second observation, as x goes away from 0, even on the negative side, right? So what happens if x equals to, so it doesn't matter, right? Because what we have is minus x square. So whether x is positive or negative, x square is going to be the same value, right? So which means whether you have x equals to 2 or x equals to minus 2, the value is going to be exactly the same, right? Which means this function is symmetric. So the first thing is, okay, let me write the conclusions here one by one carefully. The first conclusion in your Gaussian distribution is that as x moves away from mu, your y reduces. Second, it is symmetric. This plot or this function that we just saw is symmetric, right? So this is your y, this is your x, this is your mu equals to 0. Right? It is symmetric because whether you take x equals to 2 or x equals to minus 2, you're going to get the same value in this function here. Right? So the function we have here is, I'll just write it here, probability of x equals to y, which is nothing but exp of minus x square. Exp of minus x square. Again, this is the simplest form. I'm trying to explain you the bell-shaped curve here, right? The third thing is, now we know that as we move away, your y reduces. But how fast does y reduce? Remember, y is not just reducing. If y was, let's assume if y was exp of minus x. If y was exp of minus x, what does it mean? It means that it's going to reduce exponentially. Right? What is exp of minus x? It's nothing but 1 by e power x. Right? Which means as x increases, your y is going to reduce because it's 1 by, it's going to reduce exponentially. Right? But what we have here is exp of minus x square. And what is exp of minus x square? The probability of x can be written as 1 by e power x square. Which means your plot, as you're moving away from your mean, is not just reducing exponentially. It's actually reducing square of exponential because you have a square term here. So it's actually reducing extremely fast here. It's reducing really, really fast, which you'll notice better when you see this. As you move away, so this is very important. So when you go from x equals to 1, so this is x equals to 0, right? Let's look at the blue plot here, right? This is x equals to 1. By the time you reach x equals to 0, so here what value do you have? We have some roughly a value close to 0.1, right? At x equals to 1, we have a value of 0.1 for this dark blue line. But as soon as I go to 2, I almost have reached 0, which means it's falling extremely fast, right? So this bell-shaped curve actually is reducing exponentially with a quadratic function here, right? It's not just reducing exponentially, it's reducing with a quadratic function inside it, which means it's falling really, really, really fast, right? So that's one of the important properties of your PDF, that your PDF of, so as x moves away from mu, as x moves away from mu, your y reduces exponential of squared, right? So x squared, right? That is important because as you're moving away, so this is the value of x going to be. So as you're moving away, it's going to fall very, 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 very fast. Let's understand what does this fall actually mean with a small example, right? So what do we have? We have y equals to exp of minus x square, right? So if let's assume x equals to 0, okay, then what is y? Then y equals to 1 for this function. Let's not worry about probabilities. Then y equals to 1. If x equals to 1, what is y? My y is exp of minus 1, right? If x equals to 2, my y is going to be exp of minus 2, minus 4 x square, right? So let's add, what is this this is 1 by e power 1, this is 1 by e power 4. Let's look at what these values are. If x equals to 3, right, your y is going to be exp of minus 9, which is 1 by e power 9, right? Let's understand what these values are. Let's just go to Google quickly and find out what these values are. So if I say, let me just clear this up. If I just say exp of 1 by exp of 1, okay, faster, it's 0.3678, right? So it's 0.3678, right? What happens? What is 1 by e power 4? My 1 by e power 4 is going to be 0.018. It's already falling very fast. 0.018. What about 9? It's already 0.000123. Wow, I really like that number. 0.000123. So even though my x is increasing, my x here increased only by 2 times. Here my x increased only by 3 times. But look at what my y has changed. My y, literally from here to here, even from here to here, there is almost a 100x decrease, right? Because I have 2 additional decimal places here. Even though my x increased only by 1, right? This is a difference of 1.5, right? Because 2 into 1.5 is 3. But my y has increased, my y has been reduced by 100x. Now even look here, right? This is a difference of 2x, but this is a difference. This is a crazy high difference, right? Because this is, so if I do 0.18 by 0.36, right? Roughly 0.36. So 18 2s are 36. So I can just say so I could say 0.18 by 0.36 by 10. So this is 1 by 2. This is a reduction of 20x. So here is a reduction of 20x, even though this has reduced only by 2x. Even though this has, sorry, increased by 2x. Even though this has increased only by 1.5x, my reduction here is 100x, right? That's what I mean when I say exponentially quadratic drop. So if it was exponential drop, it wouldn't have been this severe. So the shape of your Gaussian distribution is it falls exponentially quadratically.